Today we're going to be looking at the difference between rational and irrational numbers. I've written some on the side as an illustration. These are examples of irrational numbers and these are rational numbers. That'll make sense to you in just a few minutes. Remember, this is what you already know. You know that there is a set of real numbers as opposed to imaginary numbers. Imaginary numbers are like square roots of negative numbers. We can do some math with them, but we can't point at the numbers on a number line. So we call those imaginary numbers. So everything else is a real number. Real numbers, one set you already know, which is why I've drawn that in there, is integers. Integers are whole numbers, negative, positive, and including 0. So apart from these whole numbers, there's also real numbers that are parts of numbers. Some of them are rational and some of them are irrational. And irrational numbers are, this is supposed to be my pretty thick I for irrational, and then rational numbers are, we often use the letter Q. Okay, so how do we know if a part of a number is rational or irrational? Integers are, by definition, rational numbers, but some parts of numbers are rational, some parts of numbers are irrational. Okay, let me write down the definition. A rational number, the word ratio is in there. A rational number is any number that can be written as a fraction of an integer divided by an integer. Right? Anything that can be written as an integer over an integer, which right away shows us that normal integers are rational, because any integer, like let's say -2, that can be written as -2 divided by 1. Right? So any integer can be written as a fraction of two integers by putting the integer on top and dividing it by 1. All right? So all integers are rational. That's why they're inside the bigger box. Irrational numbers, just the contrary, cannot be written as integer over integer. Okay. Some examples. Rational numbers, that would be, what color do I use? I'm going to do some examples. Green? For example, all fractions. All fractions are rational numbers because, like, a fraction is like 4 over 5. That's an integer over an integer, right? Okay, all integers are also in the set. We got that. All mixed numbers as well, because a mixed number is really just a combination of an integer, let's say 3, and a fraction, 3 2/3. That's an example of a mixed number, right? And the integer is actually 3 over 1, and this fraction is 2 over 3. We can combine them and turn them into an improper fraction and say this 3 is 9/3, right? And plus 2/3 is 11/3. We could write this as 11/3, which is an integer over an integer. So that goes for all mixed numbers. Now it becomes interesting. All terminating decimals, a terminating decimal is a decimal that stops somewhere. It doesn't go on forever and ever. That's a terminating decimal. This decimal can be written as 519 over 100, right? An integer over an integer. Also, all recurring decimals. This is where you might think, oh, really? Are you sure? I'm not sure. Prove it, and I will in just a minute. So 1666, you know this? Where it just goes on and gives you sixes until eternity. This is a recurring decimal. It repeats, in this case, one number over and over to eternity behind the decimal point. It could also be two decimals that are being repeated, such as 1363636, right? That's also a recurring decimal. These two can each be written as an integer over an integer. For now, you're just going to have to trust that that's true, but in 3 minutes I'm going to prove it to you. Another type of number that is rational are all square roots of a perfect square. So, no more space. So the square root of 25. 25 is a perfect square because square root of 25 is 5. Another one is 16. The square root of 16 is 4. So whenever the number under the square root sign is not a perfect square, then it's not a rational number. Then it'll automatically be irrational. That one's a little hard to imagine too. Well, this is easy to imagine, right? Because all these answers are actual integers. Square root of 25 is 5. Square root of 16 is 4. They're all simple integers, so obviously they're rational. But so whenever the number under the square root sign is not a perfect square, it's automatically an irrational number. It's not going to be a repeating decimal, recurring decimal. It's not going to be a terminating decimal. All right? So what is left? Irrational numbers. Irrational numbers are, for example, pi. Pi cannot be written as a terminating decimal. It never ends. It just goes on and on and on with numbers. It's also not a recurring decimal because, you know, as far as they've looked, and they've looked far behind the decimal point, it never starts to repeat a pattern. So pi can only be written exactly by using this symbol. Some people say pi is, 22 over 7? That's an approximation. It's not exact. So pi can only be written exact by writing the actual symbol. It can never be written as an integer over an integer. Same goes for square root of 2. 2 is not a perfect square, right? Square root of 2 is, you know, somewhere between 1 and 2, but it's a decimal and it just moves on and on. There's no repetition in the decimals and it never ends. So it's an irrational number. And this is the only exact way to write that value. You can't write it as a fraction and you can't write it as a decimal because it never ends and it never repeats. But obviously all square roots of non-perfect squares, so, you know, endless numbers, but the pi one is a big one. Okay, now I promised you that I would prove to you that you can write any recurring decimal as a fraction. So let's pick this one. 0.16666, and it goes on and on. 0.1666, on and on. You can also write this as 0.16 and write a line above the 6. Yeah? Okay, we're going to write this number as a fraction. Let's first call this number x. Now, there's one decimal that keeps repeating itself. It's the 6, right? We're going to multiply this number by 10. So we're going to calculate 10x, right? It's 10 times this, so we just move the decimal one place. 1.6, and then the 6 starts repeating itself. I'm going to write 2 of them and put the repeating sign there because I know what's coming. I'm going to write 1x underneath. That was this original number. So now you see I added a 6. I didn't add anything, but I wrote the extra 6 and put the recurring sign on top of that because now I can subtract the 2 equations from each other. I'm going to subtract 1x from 10x. So I'm going to get 9x, right? And look how nicely this works. I'm subtracting the recurring 6 from the recurring 6. That leaves me with 0, right? 6 minus 1 is 5. 1 minus 0 is 1. So apparently 9x is exactly 1.5. Cool. Now I can go and find x. X is this 1.5 divided by 9. I can clean that up. Multiply top and bottom by 2. 3/18. Oh, and then I see I can simplify by dividing both by 3. 3 divided by 3 is 1. 18 divided by 3 is 6. So x equals 1/6. So apparently this 0.16 repeating can be written as this fraction. Awesome. And this always works. Let's look at the other one I gave you, 0.3636, right? Let me write the recurring sign on top of the 2 digits that keep repeating themselves. Okay, let's do it again. We're going to call that x. Yes. Now in this case, because it has 2 recurring decimals, we're going to multiply by 100. So we're going to find 100x. Oh, I'm too slow. 100x, 100 times this, 36.36 repeating. Now, 1x is, it's actually 0.36 repeating, right? Now we're going to subtract the equations from each other. 36 repeating minus 36 repeating is just 0. Decimal point 36 minus 0 is 36. So 100x minus x is 99x. So 99x equals exactly 36. So what does x equal? 36 divided by 99. And let's make that smaller. Divide by 3 on both sides. Wait, I can do that again. Divide by 3 is 4. Divide by 3 is 11. And that's as small as it's going to get. 4/11. This repeating decimal, which actually should be written as this repeating decimal can be written as a fraction of an integer over an integer. This proves that all recurring decimals are actually rational numbers. It also shows you how to go from a recurring decimal to a fraction. So, pretty cool. Remember all of this.